get started. And if people come in late, then you'll miss a little bit of the introduction. So we're happy to have Chris Shriver. So, well, are you ready? I should ask.
I'm ready, yeah.
Okay, so we're happy to have Chris Shriver from UCLA talk about equilibrium of nearest neighbor interactions.
Nice. So I'll go over the first few slides. We'll sort of overlap a bit with what I did last week, but I'll be much lighter on the motivation, and it'll be a little more precise in some ways and in more generality than we did then. So our setup is going to include a finitely generated countable group. We'll specifically call the generators S1 through SR, and we'll always call that gamma. So that, like last week, that was always going to be integer lattice CR. And again, we can think of this as a lattice, I guess, of sites, and each of them has maybe something like a particle, which can be in a finite number of states. And this A is going to denote the possible sets of states of an individual particle, which I'll sometimes call an alphabet, maybe call them the possible spins by analogy with the Ising model. And again, a microstate is going to be an element of A to the gamma, and that specifies the state of the system exactly at a microscopic level. So there's a few features that the integer lattice has that we want to keep in mind, and the reason for generalizing in this particular way. So I've drawn a picture here. So one thing, when you imagine the integer lattice, you probably think of them being laid out in some kind of grid with even a graph structure. So I definitely want that graph structure. I actually want it to have the structure of a directed labeled graph. So here I have the blue arrows going in the positive x direction, red arrows going in the positive y direction. So I want to keep that structure. Okay, and what that structure is of course just the Cayley graph of Z, right? So I have the fixed generating set. Like I said, I was fixing generators of my group. And I want to consider the left Cayley graph of my group. So other related structure that we had before that I still want to use is that we have this sort of shift action. So of course the group naturally acts on itself, but then also that induces an action of gamma where you can shift labelings or shift microstates, right? And this sort of respects the graph structure, and that you can interpret that as recentering your view at a different point. Okay, and just a few words about the topology of the spaces we have here. So A is a finite set. We're just going to give it the discrete topology. And A to the gamma, we're going to give the product topology, which is compact, right? And actually metrizable. So good way to think about the product topology is generated by what are typically called cylinder sets. So a cylinder set is a set of microstates such that there's a fixed finite set of coordinates or sites where you only have to look at those coordinates to determine whether a microstate is in this set. And some good examples to keep in mind of continuous functions are functions that depend on only finitely many coordinates in a similar way, although there are more continuous functions than just those. Okay. So, like I said, we're going to be talking about equilibrium, and this is a thermodynamic notion of equilibrium. So we don't expect the microstate of a system to ever be eventually constant or anything like that. We're expecting to see fluctuations at the microscopic level. And a standard approach that takes this into account is to instead describe the system by an element of a probability distribution on microstates instead of a particular microstate. And we can interpret this as measuring the confidence that a system will be within this set of microstates if you were to measure it at a moment in time. And another thing I want to topology. We're going to give this the weak topology. So by that I mean it was generated by the pairing with continuous functions. So the map that sends a measure to its integral over, or the integral of a continuous function with respect to that measure, that function, all these functions should be continuous. This is also compactly metrizable. And actually there's a particular metric that I want to work with that for our purposes here, I won't need to write down the definition, but it is a transportation metric with respect to some particular metric on the space of microstates. So some of the theorems below will be stated in terms of this metric, d bar. Okay, I meant to delete that slide. Okay, so that's sort of the geometric level of the setup. Now we can start talking about the interaction itself. So basis of the definition of interaction is this function, or I guess a family of functions phi sub gamma. So this is interpreted as the energy of a microstate due to interactions involving the site gamma. Okay, so let's see. It has this first term, which by analogy with Ising model, we can interpret this as an external field. So this is only a function of the spin at gamma, right? And then all these other terms, we have functions of the spin at gamma and the spin at one of its neighbors in the Cayley graph, which is S gamma for some S that's either in the generating set or an inverse of something in the generating set. So these are the neighbors. So this is the interaction of the spin with its neighbors, and this is the interaction of it with the field. So that's more concretely what I mean by a nearest neighbor interaction. So in the particular case of the Ising model, it takes this form. And this right here is slightly different from what the way I was presenting it last week. So last week, the inverse temperature beta didn't appear in the expressions for the energy, which I think is the way I did it last week was a more physical way to do it. But this is not an uncommon thing to do, and it sometimes nicer not to have the beta floating around everywhere. Okay, so first we'll use this phi function, sort of an energy type of function to define the dynamics, the Glauber dynamics. So first we define these rate or transition rate functions, C. So this is interpreted as the propensity for the system to, for the spin at gamma to flip to the value A, conditioned on the spins everywhere else being given by X. So at each gamma, there's this transition function. That's sort of how much the system wants to transition to alpha at that site. And you can see, so because of the minus sign and the exponential there, the system wants to make flips, which will decrease the energy that way. So more precisely, we can define the Glauber dynamics using this Markov generator, which I'll call omega gamma. I say defined using, I'm trying to sweep some things under the rug, that you can't just like hit any function with this formula and have that be the definition of the generator. Because this is an infinite sum, it's not going to necessarily converge for all inputs. So what you do is you decide on some subset of functions called the core, where you're actually going to define it using this formula. And then you take the closure of the operator, and that's your actual generator. So that's just a little thing to work with, but we don't really have to get into that. Okay, but I wanted to include that notation. I also want the notation of a Markov subgroup, which is induced in a standard way from the generator. So the interpretation of this is if you hit a function f with the semigroup, so s gamma of t, then that gives you a new function whose value at x is the expected value of f if you start at x and then evolve for time t. And then using that notion of sort of evolving a function of the Markov semigroup, you can define, as I do in the last line here, the way to evolve a probability distribution according to the semigroup. And yeah, I just do that by saying what the evolved, how the evolved semigroup integrates functions, essentially. Okay, and then of course, yeah, the last line is if I start with distribution mu, then this is the distribution which I arrive at after time t. Okay. Yeah, I guess good to keep in mind, as I said last week, so there's a common interpretation of this dynamics, which is a little less formal, but you can imagine that there's some alarm clock at each vertex, which rings at exponential rate 1 intervals that are identical and identically distributed, independently distributed. And each time a clock rings, you re-randomize the spin at that vertex according to this C transition rate function. Okay, so that's the collaborative dynamics. That's this sort of this is a model for how you can imagine one of these systems to evolve over time. Okay, so something that's related is a notion of a Gibbs measure. I put equilibrium states in quotation marks because this is a notion of what it means for a state to be in equilibrium, but there is a different term called equilibrium state, which means something else. So I didn't want to just say that. So we define the Gibbs measure by prescribing certain conditional probabilities, as I've said here. So this is I'm saying that the conditional expectation, the conditional probability of finding that the spin at gamma is A, condition on the spins everywhere else being given by Y, is this transition rate function. Yeah, for all gamma and A. Okay, this is a fact which is, I think, not too difficult to show, that Gibbs measures are invariant under Glauber dynamics. So by invariant under Glauber dynamics, I'm referring to what was on the last line of the previous slide where I showed how to evolve a measure according to Glauber dynamics. So just saying that if you start with the Gibbs measure and then evolve it for any time t, you end up with the exact same Gibbs measure that you started with. So a question that's a little harder to address is, are there other invariant measures? Or if a measure is invariant under the Glauber dynamics, is it necessarily a Gibbs measure? Okay, and I guess to say it more explicitly, yeah, so the reason this is natural is because, right, I have two different notions of what it means for a state to be in equilibrium now, because I've defined my dynamics completely separately from the notion of Gibbs measures. And I would like for these to be, for this to actually coincide, the two notions. So standard way of connecting these two things that I talked about also last week, at least on the integer lattice, we can define a free energy density by this formula. So I'm letting mu subscript n denote the marginal on this box in the lattice. And in this expression here is just the free energy of the marginal. I'm dividing it by the volume of the box and then sending it into infinity. So this is, makes sense to call it a free energy density. So there's not really anything stopping me from writing this down for a non-amenable group, because I could just, I could take this lim sup over increasingly large balls in the Cayley graph, right? And since I'm taking a lim sup, not a limit, I mean, it'd be perfectly well defined. So I'm not sure if anyone has shown, or if it should be obvious, that this doesn't have the properties that we want if we define it this way, but at the very least, the proofs of the desirable properties of this quantity break down in the non-immutable case, which is, as I said, something that is pretty typical for non-immutable groups, so they're not well suited to take averages in this way. Okay, and I kind of said that last week, and I'm gonna go into a little more detail one of the properties that it has and how it depends on immutability in the integer lattice case. So this is the theorem of Holly from 71. So I haven't written explicitly, but he proved this specifically in the, well, he generalized in a slightly different way. So it'd probably be best to imagine that this is just the Ising model, not quite in the generality that I introduced before, as far as the interaction goes. So if I start with any probability measure on these Ising microstates on the integer lattice, then the free energy density, which I just defined, is a non-increasing function of time as we evolve under the Glauber dynamics. Okay, so let's say a little about the idea of the proof. So first, just write down, copy it from the last slide, the definition of the free energy density. And then I want this notation, which I mentioned before. This is just the free energy of the marginal on the cube from minus n to n. I'm gonna call that A of mu n. So this I'm calling a finite case. So it is relatively easier to show, at least it was well known how to do it at the time that this paper was written, that for finite systems, free energy is not increasing over time. So what I've written here is that if I start with this marginal mu n, which is a state on this possibly large but finite box in the lattice, so that comes with its own Glauber dynamics. And if I evolve mu n according to that finitary Glauber dynamics, then the free energy does not increase. So that I'm just gonna take for granted and say that it's relatively easy in the right framework at least. So this, in my opinion, is the key part of it that we'll come back to focus on. We'll focus on how to extend this part to the more general setting later. So I'm calling this approximate equivariance. So like I said, this is right here. If we start with mu, then we take the marginal onto the cube, and then we evolve according to the finitary dynamics. So I'm saying this is approximately the same thing as starting with mu, evolving according to the infinitary dynamics on the whole lattice, and then taking the marginal. Right. So we're just swapping which operation we do first and saying that makes not too much of a difference. Okay, and specifically what the error comes out to is when I plug this into the previous line, the inequality, I get an error that's little o of the volume of the cube. And the reason it's little o of the volume of the cube is because the boundary of the cube is little o of the volume. And the reason it's that is because the difference between, well, if I take the marginal first and then do the finitary Glauber dynamics, basically what I'm doing is I'm ignoring everything that's outside of that box that I've taken the marginal onto. That I'm only considering what's going on inside the box as far as the dynamics are concerned. Whereas over here, I haven't taken the marginal yet before I take the dynamics. So things outside the box can influence the inside of the box, but they can only do so through the boundary or via the boundary in some sense. So that influence should be controlled by the relative size of the boundary, which is the log n to the r. So that's vague, but it does end up working out that way. Okay, and now once I have this inequality, just divide by the volume, send n to infinity, and get the result. Okay, so this isn't, so I said we're gonna study free energy density as a way of connecting Gibbs measures and Glauber dynamics, right? So this particular theorem isn't quite the theorem that will do that for us, but it's, I think, looking at the proof of this is a good way to see why things work and why they break down in the non-immutable case and how we can extend things. Okay, so want to look just a little bit more about this at this approximate equivariance property. So this is just a diagram of what I was saying out loud a minute ago, that I have these two operations I can take. I can start on my infinite state, and I can pass to a finite state by taking a marginal, or within either the infinite or finite worlds, I can evolve under Glauber dynamics. And this whole diagram is approximately commutative, and it gets arbitrarily commutative the larger the rectangle is. Right. And I'm using that approximate commutativity to sort of lift this non-increasingness of free energy up to the infinite world. Okay, so we can slightly rephrase this boundary problem. So instead of just saying that it has a large boundary, instead of just saying that large subgraphs of a non-amenable group have large boundary, I can say that these large subgraphs don't typically locally look like the Cayley graph. So phrasing in terms of that problem, that so say if I'm looking at the infinite regular tree, the Cayley graph of a free group, if I take a large but finite subgraph of that and pick a vertex at random, there's a non-vanishing chance that it actually is pretty close to the boundary. So that if I look at a neighborhood of that vertex, I might actually see the boundary. So that neighborhood would not look like the Cayley graph. So, and looking at it that way, I think is helpful. And then we can borrow some of Lewis Bowen's ideas about how to extend entropy theory into the sofic world. Because entropy theory was also something which is typically, historically, you would just look at marginals on larger and larger subsets. But what Bowen did with his sofic entropy was to sort of take an extrinsic approach, to sort of take other systems which are finite, not actually subsystems, but they sort of look more and more like the infinite system. Well, we have a sequence of finite subsystems, which in some sense approximate the infinite system, and to work with that extrinsic framework. Okay, so I have a few slides now about, I'm going to go into a little more detail about what I mean by a finite system that locally looks like the infinite one, but is not actually a subset. So what we'll do is have a finite set V, which is going to be the vertex set of our finite graph. And suppose we also have sigma, which is a homomorphism from gamma, our infinite finitely generated group, into the group of permutations of V. And we can form what we're calling a graph of sigma, which just has vertex set V and has directed edges from every vertex to its images under the generators of gamma. Right. So I've drawn an example over here where I have labeled the edges according to by coloring the arrows on them, right? So in some sense, this already locally looks like the infinite graph because it has the correct number of each color of arrow coming both in and out of every vertex. But it also doesn't in another way because, so for example, here, if this is supposed to be locally like the free group, for example, we have a double edge here, which shouldn't happen in the free group, right? And then of course, we have a bunch of loops, which shouldn't happen in the free group. So we'll want to look at that too. And just a little bit of terminology. I've already been using this, I think, but I'm going to use the word finitary sometimes to specify that I'm talking about a microstate on a finite system or a state on a finite system. Okay, so that's the geometry of these systems a little bit, or like I said, actually, yeah. So now I want to introduce a particular way of quantifying the local similarity beyond just having the right numbers of colored arrows coming in and out. So the first line here is a pretty natural thing to define. This is just the fraction of vertices, so that the radius r ball at that vertex in the graph of sigma is not isomorphic to the radius r ball centered at the identity in gamma. And this isomorphism, the isomorphism we're looking for or asking about, should respect edge directions and colorings, labelings. Okay, so the second thing is obviously a little more ad hoc. The exact constants that appear are just ones that fit the theorem that I was able to prove. But the point is that this quantity is small if the graph of sigma looks like the graph of gamma to a large radius near most vertices, right? So I can make this small by making r large, as long as making r large doesn't make this too big. Anyway, so these two competing terms. Okay, and if you're familiar with this kind of thing, then this is a sofic approximation to gamma if and only if this quantity goes to 0. So sofic approximation is you're supposed to be asymptotically free and asymptotically in action, right? So I'm already only considering sequences that are actions, assuming they have homomorphisms, and this condition will make it be asymptotically free. Okay, and then the point is that there does exist such a sigma for many non-amenable groups. So for example, FR can be approximated by finite systems in this way. So if we can work with these finite systems instead of finite subsystems, then we'll be able to extend results from integer lattices to FR. Okay, yeah, so that's all the stuff about sort of the geometry of these systems and comparing them to the infinite ones. So I need to say a little bit about how the interaction will work on the finite subsystems. So this is actually a little bit easier to do in the finite case because we can define this internal energy U. So again, we could write down basically the same thing in the infinite case, but it would not necessarily converge. So that function that I had before, phi sub gamma was a notation then. That's just if you take this expression, but then get rid of all the terms that don't include gamma, or maybe some v in this case. So in the finite setting, a Gibbs state is just a probability measure, which is proportional to exponential minus the energy. And that definition comes from that measure being the unique minimizer of the free energy. So thermodynamically, in the finite case at least, this is the fundamental quantity, is the free energy. And you can calculate that the Gibbs state is the unique minimizer of that. Okay, so we have the Gibbs states, we have the free energy. The last thing I say something about is the Glauber dynamics. And this is really, yeah, so these transition rate functions here, the definition looks different, but the point is that it has the same relationship to Gibbs states as we did in the infinite case. Right?
Could I interject something?
Oh, sure.
I mean, it seems to me that this trick can vary, can change the dynamics a lot, because if you think about, say, just a Ising model on a free group with constant magnetic field. He says, you know that if the magnetic field is 0, then at low temperature and maybe even at high temperature, I'm not sure, you're going to have two Gibbs states, one where almost everything is spin up, and one where almost everything is spin down. Now, if you make the magnetic field slightly positive, it's still going to be the case that everything spin up and everything spin down are local optima of the free energy. Because if you try to change the spin over a big block, the boundary region where you go from that to the background is huge. And so the energy cost of having things mismatched on the boundary is going to be bigger than the energy gain you have by making the interior region go to the favored direction. And so the Glauber dynamics on the infinite group is still going to have these two different Gibbs states. On the other hand, if you approximate it with a finite setup, then no matter how small the magnetic field is, having something where most things are spin up is going to be preferred to having everything with spin down. And so you're only going to be able to get you're only going to find one Gibbs state.
Well, there's always only one Gibbs state in the finite setting, right?
Well, exactly. There's only one in the finite setting, and you're only going to, if let's say you have magnetic field up, you're only going to see the limiting situation where everything is spin up, or almost everything is up, spin up plus small.
Oh, you're saying if you take the limits of the Gibbs states on the finite graphs,
I'm saying that in the infinite thing, you have two Gibbs states, but you can only achieve one of them as the limit of what you get on these finite regions.
That's true if you only take limits of Gibbs states on the finite graphs. But you could take limits of other states on the finite graphs, which might be, in some sense, like metastable, which could converge to the other Gibbs state.
Right. Well, states are states, but you're but in terms of what the dynamics is pushing you towards, in the finite state, you're only seeing one kind of large scale situation where almost everything has spins pointing in the correct direction. While if you started with the infinite system and started off with all the spins being spin down and let the Glauber dynamics run for arbitrarily long time, you're still going to have everything being spin down and you'll never get to spin up.
Right. So in the infinite setting, you can have actually another Gibbs state where it'll stay there forever. So the analog in the finite setting, so if your external field points up and you start with something pointing down, if you run that, so like for an infinite amount of time, then eventually you'll get to the Gibbs state, which is something else. But
in the finite setting.
It's right in the finite setting.
Right, but not in
but if you start with down in the finite setting, you can still run it for a really, really long time, just not a really, really, really long time, and you'll stay mostly down. So it's metastable in that sense.
Yeah, yeah.
It's not, but that's, yeah. I don't know, is that it?
Right. It just seems that this is going to be some sort of fundamental barrier to trying to draw equivalences because because there is this infinite state, that there isn't a Gibbs state of the infinite system that, it's a stationary point of the Glauber dynamics, it's a Gibbs state, but that is not approximated by any sort of Gibbs state in the finite system. And so the game of let's understand these infinite states by viewing them as approximations of finite states, maybe you figured it out, but it looks to me like there's something missing.
Well, there's still a number of slides left, so hopefully if there's something missing,
okay.
I'll fill in then. But we can definitely talk about it more later. That's
fair enough.
Yeah, okay. Yeah, definitely tell me later if you think there's still something that's fishy. Okay, so now I start working towards the correspondence between infinite and finite states. All right, because that's the big thing that's lost when we go to the extrinsic view. So we've gained the ability to have local similarity to the infinite graph, but we've lost this natural operation of just taking the marginal. Okay, so this operation is right here. This directly from the ergodic theory literature that I was mentioning before regarding sofic entropy. So if I have this finite system, which is on the right, and I have some labeling X, so our finitary microstate X, which is just a labeling. I've drawn here just a few labels, and I've picked a base point V. I can just lift the labeling I can lift that labeling to the infinite graph with the base point V, so starting at V. So all I'm going to do is I just take the label at V and I put it at the identity, and then from there on out, I just follow the arrows. So here, this blue I put here because it was at the start of a blue arrow, which goes into V. So I put it at the start of the blue arrow, which goes into the identity, and then so on. That red dot was at the end of a blue arrow coming out of V. So I put at the end of the blue arrow coming out of the identity. And yeah, I guess one thing to point out is that I did lift this blue dot to two separate locations because of this double edge here, right? So there's both a blue and a red edge there. So I lifted it there and there. Okay, and I can call this the pullback name or the lift, and the formal definition is, I think that's about the only reasonable place to put all the involved symbols on the right-hand side of that equation. Okay, so that was how we lift or form a pullback name. So empirical distribution of a finitary microstate over sigma is just the distribution of these lifts or pullback names that you see as the base point varies. So one way to write this is just to push forward the uniform measure on V under the map, which sends the vertex to the lift based at V. Equivalently, if you plug in a set E, then the measure the empirical distribution gives to that set is the fraction of vertices that the pullback based at V is in that set of microstates. Okay, so mentioned a little while ago, we were considering the weak topology on the space prob of a to the gamma. So microstates with weakly close empirical distributions have similar local statistics, is the way to think about it. And the locality is coming from the way the weak topology works. So like I was saying, a weak topology kind of mostly looks at finite subsets, right? And convenient notation that we'll be using is P to the sigma as the function which sends a microstate to its empirical distribution. Okay, so this is also something which you can find in ergodic theory literature on, say, like the F invariant or sofic entropy, some approaches to sofic entropy. Okay, so this is maybe less common, or maybe it's already been written down, I don't know. But I also want to talk about the empirical distribution of a state, of a probability measure on microstates. So this is just the expected empirical distribution of a random microstate, which is distributed according to zeta. And then here's a few different ways of writing that down. And you can kind of interpret this as saying that states with weakly close empirical distributions are going to have similar average local marginals. So I'm interpreting this expression as averaging local marginals of zeta. And again, locality is just coming from the definition of the topology. Okay, so that's the empirical distribution of a state, just looking at local statistics. So this theorem is saying that the empirical distribution operation has the desired approximate equivariance that I was talking about before. So bit of a mess of symbols, I guess, but this is what's going on, right? Again, I have these two different operations. I have the empirical distribution, which is going from finite states to infinite states. And I've got Glauber dynamics, which is going within finite, within infinite. And it approximately doesn't matter which order I do these things in. Okay, and then here, this parameter is coming up where it matters less and less the closer my finite system is to being locally similar to the infinite one, right? And then of course it matters how long I want this similarity to persist for, right? And this is the shape I was able to get for that dependence. Okay, so this is approximate equivariance, and unfortunately it does go in the wrong direction, or at least the opposite direction I did before. So this is not going to ruin everything, but it's going to make us do things a little bit differently, at least, right? So I have a way of going from the finite world to the infinite world instead of vice versa. So I also can't just literally invert the map. That's not going to work. But what I can do, because I do still want to start with a state, with an infinitary state, instead of projecting down to some fixed finitary state, I can look at the collection of finitary states whose empirical distribution is close to the infinitary state that I'm starting with. So these are ones that are locally consistent with that one. So here's a precise definition of that. If I have some open subset of infinite states, so probability measures on a to the gamma, I can say that a finite state is an O state if its empirical distribution lies in O. Okay, and I guess the O state over sigma if I want to specify the dependence on that. So if O is a small neighborhood of mu, we can interpret this as saying that zeta is consistent with mu as far as local statistics are concerned, and then O is kind of a quality parameter for this consistency. And then this notation is what I'm using to denote the set of such states. So they're kind of good finitary models for the infinite thing, right? So yeah, even if mu is a Gibbs, state, like it might have things in here which are not finitary Gibbs states, right? So that's how I'm gonna deal with that. So there is this possibility, which is gonna keep coming up through the rest of the talk, that this could be empty, right? So in particular, you can check from the definition I've been using that empirical distribution is always shift invariant. So if O doesn't contain any shift invariant states, then this is going to be empty. Okay, but that's not the only thing that can go wrong, as we'll see later. Okay, so now I can define my free energy density, or at least so some version of free energy density in the setting. So I have my state, which I want to measure the energy density of. I fix a particular approximating sequence, sofic approximation, sigma. Okay, and I need to have this going to 0, which is what makes it a sofic approximation, as I was saying before. Okay, so what I have here that's not faded out, this is sort of the thing that you'd expect to see from before. I'm taking some free energy of zeta, which is going to be a finite state, when divided by the volume and taking n to infinity. And then the way so yeah, I guess I'm not actually picking a particular state. Like I said, I'm looking at a set of states that are they're O consistent with mu. And yeah, I'm not picking an individual state. The quantity I'm putting here is just the infimum of all the possible free energies of O consistent states over sigma n. So I'm putting that there, then I'm taking n to infinity, and then I'm letting O shrink down to mu. Right, and this is my free energy density relative to sigma. Okay, and then I have this ghost autonomy over here about the possibility of set being infinite. And the way I'm dealing with that is the convention that the empty set has infimum plus infinity. So yeah. that was not possible in the ZR case. The ZR, there was always uniform upper and lower bounds for free energy density, and now we have to deal with this plus infinity thing. Okay, so there's one more slide with a bunch of stuff on it, and then a few more shorter things. So I want to say a little bit about this, which is the analog of the theorem that I said some more about the proof in the integer lattice setting, is that free energy is non-increasing. So I've introduced here a slightly compact notation for the collaborative dynamics. So mu sub t is the evolution of mu. And implied here is that for any choice of sigma, this is true. Okay, and then again, starting the proof by just reminding of the definition. So I have here a picture of what's happening with this approximate equivariance. So this is a starting situation. I have some finitary state zeta naught, and its empirical distribution is within some neighborhood of mu naught, right? And if I let things evolve over time, then I can see the empirical distribution after time t is within some slightly larger neighborhood of mu t, right? So this, to be clear, this is not the evolved empirical distribution. This is the empirical distribution of the evolved measure, right? Those are slightly different. Okay, and then a more precise version of this picture is this statement. So the distance between the final two measures is controlled by the initial distance and how close the finite system is to approximate the infinite one, which is what this term comes with. So this term is important because it allows us to control the difference between evolving the empirical distribution and tracking the empirical distribution as we evolve the finite one. Okay. Okay, so this picture in mind, we're gonna go slightly backwards. So we're gonna start at the end point. So suppose that we're given some neighborhood of mu t, which is ut. What this picture is trying to tell us is that we can then pick a small enough neighborhood of the starting measure so that this picture holds basically. So that whenever the empirical distribution starts in u naught, it ends in ut. And then there's the qualification for all large n, because we need this term to be small also. Okay, anyway, so the point is that, yeah, we can ensure that this picture holds. And now we invoke the finite case just as before. So if I start with any finitary state zeta, then its free energy is at least the free energy of the terminal finitary state zeta t. And since we know that its empirical distribution is in ut, we know that zeta t is in this set. So that's just definition of the infimum. Okay, and then we take the infimum over choice of zeta naught, and then we divide by the volume and take the remaining limits in the correct order, and we get the theorem.
So can I ask you a question?
Yeah.
So when you write d bar here, are you thinking of the d bar distance in in terms of joinings of measures?
Yes, yeah.
Okay.
I am, yeah, but I didn't say what the metric on a to the gamma was that I was using, though, but there is a particular one that I have in mind.
Okay. Okay, well, that's still, okay.
But yeah, it generates the weak topology.
Well, it generates a stronger topology than the weak topology.
I don't think it does in this case. Maybe we could talk about that at some point, if you think that's true.
Yeah, like ergodicity is closed in the d-bar topology, but it's not closed in general.
It might depend on, specifically, and I don't know, I would be interested in talking about that.
I mean, yeah, I mean, yeah, well, I mean, I guess the conclusion is that using d-bar distance is going to give you stronger results if you can prove inequalities like this than using some other, because it's a stronger topology. Anyway, sure, we can talk about it afterwards.
Okay. Okay, so that's the version of this theorem, which again is not exactly what we want, but I think demonstrates things a little bit. Okay, so I have two other things I want to say, which are the refinements of this theorem, which actually prove the things that I wanted to prove, equivalence between different notions of equilibrium. So first of all, if I start with a state which has finite free energy density and is not Gibbs, then the free energy strictly decreases over time. So this means that any state which minimizes the free energy density has to be a Gibbs state. And one detail to that is that there always do exist, for any sigma, there are states that have finite free energy density. So the minimizers have to have finite free energy density. So the converse to this is true in the ZR setting, but at least for degenerate reasons, it can't be true in this setting because there do exist Gibbs states and choices of sigma, so that the Gibbs state has free energy plus infinity. I don't know if it's possible for a Gibbs state to have free energy, which is finite but not minimal. Okay, this one is my favorite. So again, if I start with something which is finite free energy density, then as t goes to infinity, we approach the set of Gibbs states. And so what that means is if you take any weakly open neighborhood of the set of Gibbs states, then eventually the dynamics is contained within that open set. So a corollary of this, which is that if I restrict to the case of the free group, then if I start with any shift invariant measure, then mu t approaches the set of Gibbs states as t goes to infinity. So Bowen helped me with this a little bit by pointing me to this property PA, which he studied a while ago. So any group that has property PA, this corollary works for, and FR is a particular example. So the relevant formulation of this property in this setting is that for every shift invariant mu, there is some sigma which assigns finite free energy density to mu. And I kind of mentioned before that shift invariance is a necessary condition because empirical distributions are always shift invariant. So this property allows us to always pick an appropriate sigma, no matter what starting point we want to study. Okay, that's what I've got. Thank you.
Okay, great. Right, so there are questions for Chris. Yeah, so thanks for the interesting second part to your two-part series. So, I mean, I guess what you're doing is you're when you evolve by Glauber dynamics on a finite setting, it looks like the order of the limits matters. So you evolve up to time t, and then you're taking this, but you're not sending t to infinity. You know, first you send the finite approximations to infinity, and then you send t to infinity. Is kind of the order of it. I mean,
you could put it that way.
I'm trying to try to give an explanation to what Lorenzo was asking about. Is that in some sense what you're is that you're taking the approximation, you know, the finite approximation is you're taking the limit there first as that approximation gets better and better to the geometry of the system. And then afterwards, you're taking a limit as time goes to infinity. If you did the opposite order, then you would be in trouble, and you know things wouldn't be as interesting.
Right, and because of the order of the limits that you said, you can find yourself in a Gibbs state that doesn't maximize free energy.
In the infinite?
Yeah, I mean, it just, I mean, by taking the approximants getting bigger and bigger and bigger faster than you're taking t goes to infinity, you know, that's a hand-wavy statement, but you know what I mean. You can get the state where almost everything is spin up or spin down, or you know, either spin up or spin down from that Ising model. But those two states have different free energies. You know, and they're both achievable, but they have different free energies. And the one with the lower free energy doesn't maximize free energy, but it's still a perfectly good state. You know, it's still a fixed point of the Glauber dynamics.
Yeah.
It's a local optimizer of free energy, and you know, the way that you have your approximations getting bigger and bigger and bigger, you aren't allowing yourself to probe the things that are very, very far away, and so you can get trapped in it. And that makes sense.
So, oh, right. So we spoke once before, and I was asking whether or not Gibbs states are Markov measures in some sense for the free group.
Oh,
Did you, just curiosity, have you?
So yeah, Georgie's book has a chapter on this. So they're always Markov random fields, but they're not always Markov chains. So the set of Gibbs states is a convex set, and the extreme points of it are always Markov chains. But in general, there can be Gibbs states that are not Markov chains.
Oh, okay.
He gives a construction for a proof that this can be possible for the Ising model on a tree.
Okay. Okay, that's very interesting.
I get possibly related to the earlier discussion. So the way I've been thinking about this is that I'm sort of only allowing the finitary dynamics to evolve an amount of time which grows linearly with the size of the set. And the mixing time can typically grow exponentially with the size of the set. So maybe that's another way of putting the same thing. And I'm not letting it grow. I'm not letting the dynamics go long enough to always reach the true equilibrium.
Mm-hmm.
That's another way of putting it. Linearly, because, well, yeah. But yeah, maybe there's some interesting things to say about that. That you can get to something which is sort of locally Gibbs in a linear amount of time, but not the actual finitary Gibbs state.
Right. Yeah, okay. Well, thanks. So I don't know, we should thank Chris again for a nice part two.
Thank you for having me.
And yeah, I don't know what to say. So if there are no, well, if anybody has a question, ask now. And otherwise, I think we'll end it.
Great, thanks.
Okay, great. Thanks again. And
bye.
Have a good one.